What's the polarity of that magnet? Which end is north and which end is south? Left side is north, right side is south. How do you know that? Magnetic fields go away from north, magnetic fields go toward the south. If I was to put a compass right here at this spot, which way would the compass point? Which way? Okay, good answer. Towards the south. That's not what I was looking for, but it's a good answer. Toward the south. I'm looking for a specific direction at that spot. Okay? It would point in the direction of the field, and at that spot, that's up that way. So technically, I guess it's not really toward the south, at least not directly toward the south. But the field line, if we look at it as a bigger field line, it does absolutely then go towards the south, from north to south. At this point, the field line would point this way, so the compass would point in this direction, right? Which way would the domains point? Those domains, those things that are aligned here, because we have a magnet, right? Not just a non-magnetized ferromagnetic material, but rather we have a magnet. Which way would those domains point in this magnet here? They're going to point towards the north. Yeah, they point from south to north. It's like an extension of the field lines. If we keep going around like this, it goes around in a full circle, right? Domains go from south to north inside the magnet, and then the magnetic fields outside go around from north to south, of course. All right, let's try another picture here. What's the polarity right here? It's going to be a south, of course. What about right here? How do you know it's going to be a north? I don't have any field line directions drawn. How do I know that's going to be a north pole? Yeah, the shape of the field tells us that these have got to be like poles, right? The fields are repelling each other right here in the middle. So that's got to be a north pole, and therefore that's got to be a south pole. What about directions now? Which way is the field line going to go right here? To the left or right? Right here? It's going to go to the left, from north to south, right? Which way is it going to go right here? It's going to go to the right, from north to south again. Good. Now let's go one more here. You probably know more or less what this one's going to look like. What's the polarity of this magnet right here? That's going to be a south. How do you know that? Field lines are pointing towards the south. What's the polarity of this one right here? It's going to be a north. There's two ways that you know that. How? What's one of them? Field lines go away from the north and they go towards the south. What's the other way that you know that's going to be a north, given that this one is a south? It's tracted, yeah, it's the shape of the field, right? As long as you know that this one is a south, then you know that this one's got to be opposite because of the shape of the field lines. Good. We got a couple more. Here, let's label this as north and let's label this as south. A couple more field lines to draw. Which way is the field going to point right here above this first magnet? To the left or to the right? To the right, because it's away from the north and toward the south. And which way is the field line going to point right here? It's also going to be to the right. It's going to be away from the north and toward the south. Good? Good. All right. On Friday, we talked a little bit about the discovery of the relationship between electricity and magnetism, or at least the first discovery, the first relationship between electricity and magnetism. Here we are almost 100 years ago. Hans Christian Ørsted discovers by accident that an electric current will generate a magnetic field. Essentially, he's got a compass, he's got an electric current going, and he finds, oops, the compass doesn't point north anymore. Or, which way does the compass really point? Towards magnetic south. So he finds that the compass doesn't point towards magnetic south anymore. It points in some other direction. He flips the electric current off, and all of a sudden the compass goes back to pointing where it's supposed to point, towards Santa Claus's house. Flips it on, and then it points in some other direction again. His only conclusion could be that that electric current was generating a magnetic field that was messing up that compass. In fact, that is the correct assumption. That's the correct analysis of that. This turns out to be, and you're going to see as the unit goes on, this turns out to be probably one of the biggest discoveries, one of the biggest science discoveries ever. because this ends up being in just about every piece of technology that we have today. Okay, if we didn't have this discovery, then we would have virtually nothing in terms of the technological things that we use today. Okay, the idea that electricity generates magnetism. Now, I told you on Friday we learned today what that magnetic field looks like. It's not quite as simple as just drawing a picture of a bar magnet and knowing that the magnetic field is always in the same direction from north to south, and the shape of it's always the same. Okay, the shape of this is a little bit different, and the direction has to be found by using this kind of newfangled rule that we'll teach you in a few minutes. Oersted would have discovered in 1919 that the magnetic field is always the same shape surrounding a wire that carries an electric current, but it's a completely different shape than we see surrounding that bar magnet. The shape is always circular. Now, before I show you what exactly looks like, and before I show you how we find out the direction, I want to define a couple of things here. Not terms, but rather symbols. If I draw an arrow to the right, then that means something, some kind of vector, something is pointing to the right. Maybe a velocity is to the right, maybe a force is to the right, maybe an electric current is going to the right. If I draw it downwards, left, up, we know what that means, right? Okay, whatever is pointing downwards, left, or up. But how do we draw, if an electric current, for instance, charged particles are moving into the page or out of the page, coming towards you guys or going away from you guys? Let me tell you a quick little story to help you to remember the symbols that we're going to use for into and out of the page. When I was, I think I was about 4. I don't think I had started school yet. I was playing in my friend's house across the street. He was a couple of years older than I was, but we were in the house across the street, his house, across the street in the basement, where we played fairly often. Anyways, I remember he had a pool table down there, and that was kind of fun for 4 or 5-year-olds. He also had a dartboard down there, and we used to play darts every once in a while. Not often, because we weren't very good, but every once in a while we'd play darts. This one day I remember it very clearly still, even though I was only 4 or 5 years old. We're playing darts. Of course, you're throwing the darts at the dartboard at 4 or 5 years old, and if you happen to hit the board, okay, then you get lucky. Right? If you happen to stick it in the board, then it's even luckier, because it rarely happened at 4 or 5 years old that we even hit the board, let alone stuck the dart in the board. I remember I threw my 3 darts, threw it at the board, threw it at the board, threw it at the board. I don't remember if I hit the board or not, but I know I didn't stick any in the board. I remember walking over to pick up the darts that are sitting beside the dartboard. I bend over, I stand up, and all of a sudden, thought, there's a dart that my friend, who's a couple years older than me, threw, missed the dartboard, but hit me and stuck in my back, literally stuck in my back. I think I might have even cried that time. I think that might have been the last time I cried when I was 4, but I think I might have cried that day. What does that have to do with this? Well, I didn't see the dart coming towards me because, first of all, I was facing the other way. Second of all, even though it's a 6 or 7-year-old throwing a dart, it's moving too fast in order to really see details of the dart coming towards you. But if I could see it, I can in my mind see it, even though I don't really remember the dart coming towards me. I can in my mind picture in slow motion this dart coming towards me. When I see this dart coming towards me, I see kind of a dot. Right? It's the tip of the dart coming towards me. It's a dot, right? If I picture this dart going away from me, which is the way I'd rather picture it, going away from me as opposed to towards me, then what do I see? I see the fins of this dart, or the feathers of this dart, that kind of look like an X. We're going to use a dot to represent whenever something is coming towards us. If a car is coming towards us out of the page, then we'll represent its velocity by a dart, or sorry, by a dot. Sorry. If it's going away from us, we'll represent it by an X. If an electric current is coming out of the page towards us, then we're going to represent it by a dot. If it's going away from us, we're going to represent it by an X. Got it? So now we've got right, left, up, down, into the page, and out of the page. We can represent any direction now, in not just a 2-dimensional okay, system of representing directions, but now we have a three-dimensional system of representing vectors. So now that we have this way of describing which way things are moving, if they're moving into or out of the page, I want to show you what the magnetic field looks like surrounding an electric current that is going this way. Which way is this again? Into the page or out of the page? Out of the page. Remember, you're picturing that dart coming towards you. It's a dot, right? It's the tip of the dart that's coming towards you. Not the end of it going away from you where you see these fins represented by an X. It's the tip of the dart coming towards you. We said the shape of the magnetic field is circular. So we're going to draw like this. Pay really close attention not only to the shape of it here, but to the spacing of the magnetic field lines. There's lots of magnetic field lines that surround a charged particle or an electric current that's coming towards you, just the same as there's lots of magnetic field lines that surround a bar magnet. Just a different shape, that's all. What do you notice about the spacing of these magnetic field lines that are all circular? What do you notice about the spacing of them? They're getting bigger, yeah, and they're getting further apart. That tells us the density of the field lines represents how strong the field is, right? How close the field lines are together tell us how strong the field is. When we have field lines that are further apart from each other, that tells us that we have a weaker field. And that should make sense to us, right? If this wire that's carrying this electric current is generating a magnetic field, then the further you get away from that wire, the weaker the field you're going to have. Just the same as a regular bar magnet. The further you get away from the magnet, the weaker the magnetic field is going to be. We're on the surface of the Earth. We're a long way from the core of the Earth, the place that generates the Earth's magnetic field. When we're this far out, the magnetic field strength caused by the Earth is pretty weak. Okay, it is here too. The further you get away from the moving charge, the weaker the field is going to be. Now, how are we going to determine the direction of this magnetic field? Here's what I want you to do right now. Okay, I want you to take both hands. Okay, put them up. I want you to put your left hand in. I want you to put your left hand out. I want you to put your right hand in. And I want you to shake it all about. Then I want you to, no, never mind. We'll stop there. You're going to use your left hand for this, but there are going to be times where you use your right hand. So have both of them ready. When it's a negatively charged particle, okay, let's say an electron, you can use your left hand. When it's a positively charged particle, like a proton or an alpha particle, you're going to use your right hand. Got it? Negative, left, positive, right. It's kind of like the convention that we use for direction, right? If it's going to the left, it's a negative part, or it's a negative direction. If it's going to the right, it's a positive direction. It's a different system here, but it can help us to remember when we use the left hand and when we use the right hand. Negative particles, left hand. Positive particles, right hand. Here's what I want you to do with your left hand right now. I want you to stick your thumb this way, towards the back of the room, okay? Out of the plane of the page, right? In the direction that the particle is moving. So always stick your thumb in the direction that the particle is moving. And then I want you to clench your fingers. You don't have to clench them like, really, really tight, like you're making a fist to hit somebody, but just clench them a little bit. Okay, there's no rule on how much you clench them, so don't worry, you can't do this wrong. If you can't clench them too far, you can't clench them not enough. Okay, just clench your fingers a little bit. Okay, the way that your fingers point is the way that the magnetic field points. So right here, the way that I have my fingers represented right now, my fingers are pointing directly to the right. So I'd say the magnetic field is to the right. But then somebody else may have the fingers clenched more and say, oh, my fingers are pointing downwards right now. That's okay. Because to the right, my fingers right now are to the right of the particle, and to the right of the particle, the field points downward. So it doesn't matter how far you've got your fingers clenched, they will point in the direction of the magnetic field. Okay? Turn your hand around a little bit like this. Right? Thumb, particle, fingers. Well, it should go in a circle, right? The field should be circular around the moving charge. Does that make sense? Is that okay, guys? So thumb, fingers, doesn't matter where I put my fingers again, as long as I have those fingers kind of clenched a little bit so that they're not straight out. Okay, we can figure out which way the field is, no matter which way my fingers, no matter where my fingers are there. All right, let's draw another one. let's say that we've got an electric current, electrons again, going which way? These ones are going into the board or into the page, away from you guys. Now, you can have the same symbol on your page in front of you, except, of course, the page isn't vertical like it is for me. It's horizontal. Okay, no big deal. Okay, if it's into the page, into your page, then you stick your thumb, okay, into your page, just like that. Okay, for us, it's into my page, so we're going to stick my thumb towards the front of the room. It's a left thumb because it's negative particle. Okay, we know the magnetic field surrounding it is going to look something like this. The only question is the magnetic field clockwise, like it was here, or counterclockwise? Thumb, fingers are pointing which way? Counterclockwise. So the magnetic field here would be counterclockwise. Got it? So you can see how if Oersted is playing with an electric current, doing some kind of experiment with an electric current, brings a compass nearby, you can see how this would completely mess up the direction of his compass. Okay, instead of pointing towards magnetic south like it's supposed to, it's going to be messed up by these field lines that are caused by these moving charges inside the wire. If you've already written down a little note on this as I described the rule that I just showed you, that's fine. You don't need to write down this page. But understand that we're going to call from now on, we're going to call this the wire grasp rule, because it's like we're grasping a wire, right? Thumb in the direction of the current, grasp the wire. Clench your fingers in the direction of the magnetic field. Okay, our fingers will point in that direction of the magnetic field. You don't need to draw this if you've already written something down, but if you haven't, then maybe see what you can do about writing this out, and then, if you can, kind of draw that picture. Okay, whatever works for you, though. You need to have something written down, but not necessarily this page. All right, so let's do a couple examples. Two of them we've really already done, but we're going to do them again, and then one of them we haven't done. The first one is, let's change it up a little bit. Let's say that this is an alpha particle, which, of course, has a charge of 2+. We'll just make it a positively charged particle, represented by this x. The x means which way? Into the page. Okay. The x means into the page. So if we have an arrow pointing like this, it means to the right. This means up. This means down. This means left. The x means into the page. The dot means out of the page. Remember, you're picturing it as a positive particle that's going into the page, or you're picturing it, I should say, as the back of a dart going away from you. Okay, the way the back of the dart looks. The x. Draw the field lines around there, or at least a couple of them. First field line, second field line, third field line. They get progressively further and further apart from each other. Field strength gets weaker the further we get away from this alpha particle. Shape of it, circular. Direction, which hand are we going to use? You're going to use the right hand because it's a positive particle. Listen, I've told you just about every day there's been something. Just about every day since the beginning of class. There's been something that we should circle in red or draw attention to. Even though this is positive, and we normally deal with positives up until now, and stuff, we should draw attention to this. Because you can imagine how easy it is to miss the right hand versus left hand. You use the left hand rule when you should be using the right hand rule, or you use the right hand rule when you should be using the left hand rule. Okay? Every time you see a question involving a hand rule, you should circle the type of particle that it is, and then write in RH or LH to remind you which hand to use. This is the right hand because it's a positive particle. What do you do with your right thumb? Stick it into the page. Thumb in the direction of the particle, which is into the page, just like this. Just like you see my thumb right now. My fingers are going to be kind of clenched. You can see that my fingers are going which way? Clockwise or counterclockwise? Clockwise. So the magnetic field is going to be clockwise, surrounding that alpha particle going into the page. We're going to make this one an electron, so it's a negative particle. Probably should still circle that. Write down that it's a left-hand problem because it is a negative particle. Draw a magnetic field that surrounds it. It's going to be circular as well. Field lines are going to get further apart from each other. Shape. Now let's take our left hand and stick our thumb which way? Out of the page, yeah. Thumb out of the page. Okay, fingers are going to go clockwise. How can the answer be the same? The particle is moving opposite to the last one, but yet the field is the same? How is that possible? It's a different charge. Okay, if a positive going into the page causes a clockwise field, then a negative coming out of the page would produce a clockwise field. Now, what about this one? You've got an electron that's moving to the left. I want to find the field above this wire, below this wire, in front of this wire, and behind this wire. It's technically no different the way that I do this, but it is a little bit harder for most people at least to see the answer here. This meter stick is going to be my wire, okay? It's going this way. The current is going this way in the wire towards the left side of the room. Got it? Which hand do I use, by the way? Left hand or right hand? Left hand because it's a negative particle. Stick your thumb in the direction of the particle, which is toward the left side of the room. That's easy so far, right? Okay, it doesn't matter whether I put my thumb in front or the thumb behind. It doesn't matter where I put it as long as I've got my thumb pointing in the right direction. Okay. Now, take a look at, when I clench my fingers, take a look at right now where my fingers are. Don't worry about which way they're pointing. Where are the tips of my fingers, my fingernails? Where are they relative to the wire? Are they below the wire? No, they're above the wire, right? So look at my fingertips. Okay, look at my fingernails. Right now, they're above the wire. Which way are they pointing? If this is the plane of the page, which way are my fingernails pointing? Out of the page, right? Towards you guys. So above the wire, we would say the magnetic field is pointing out of the page. Let's say now, where are my fingers right now? Okay, I can put them wherever I want. Okay, I want the magnetic field above, below, in front, and behind. So let's put my fingers in those 4 places. Right now, my fingers are where? You're looking at my, not my whole fingers, right? They curve and they're everywhere, right? But my fingernails, where are they? They're below the wire, right? Which way are they pointing? They're pointing into the page. Now, take a look at where my fingers are right now. Not which way they're pointing. Where are they? My fingernails, where are they relative to this plane of the page, relative to this wire that you see here? They're in front of the wire, right? My fingers are in front of the wire. Which way are they pointing? Shanae, which way are my fingers pointing? Sorry? No, my fingernails right now. Which way are they pointing? They're pointing down toward the floor, toward the bottom of the page. If this is the plane of the page, right? They're pointing down towards the bottom of the page. You guys see that? Can you guys all see that? So in front of the wire, my fingers are pointing down. And behind the wire, yeah, this is when it starts becoming fun actually for me. Once you learn this hand rule well, and then once you learn another hand rule tomorrow, then it becomes interesting to see for me to see you starting to try to contort your bodies to try to get your hands in the right places. So, for instance, my fingers here need to be behind the wire. So you start doing this, right? This, and then you start, wait a sec, my hand doesn't move that way, so you gotta do this, or whatever. Okay. My fingers are behind the wire right now. Okay, behind the wire. Which way are they pointing? Up. Yeah, up toward the top of the page. Does that make sense? It's pretty difficult to draw it on this one like it was on the first two examples here, because just the nature of it. You start trying to draw it, and it's like, wait a second, how do I draw the magnetic field surrounding that? It's easy surrounding the first two. Not so easy there, but as long as you can describe it in words, that's fine too. Any questions on that? All right. What I would like you to do then is to take a look at the first 6 questions, which would be the only 6 questions, on worksheet number 10, which I'm going to give you right now. With every question you see on this worksheet, first of all, number 1, before you do anything else, circle, identify whether it's a negative particle or a positive particle, and then write down LH or RH to remind you which hand you're going to use, okay? You can be really good at these hand rules and really good at all the stuff we've just done, but if you make a mistake with the hand that you use, then it's all for naught. Okay? It means nothing because you're going to get the exact opposite answer that you should. So circle circle negative or positive. Write down LH or RH or whatever it needs to be, okay? And then go to work with the actual hand rule. All right, let's take a look at worksheet number 10 now. Question number 1 said we had an electron current represented by the X. Circle electron. Okay, you know it's a negative particle. Circle electron and write down, just small letters, write down LH to remind yourself that you're going to use your left hand. Now, is that electron going into the page or out of the page here? It's going into the page. So we're going to stick our left thumb into the page. Fingers are going to go which way? Counterclockwise. So we'd say counterclockwise for question number 1. Or you could draw it as counterclockwise. Doesn't really matter. 2, we have an electron current again. So before we go any further, electron we're going to circle in red, and then we're going to write down an LH, reminding us that we're going to use the left hand for that. It's represented by a dot, so that means it's coming out of the page. So we're going to stick our thumb out of the page. Fingers are going to go clockwise. Clockwise is our answer. Now 3, this is where it starts becoming a little bit trickier. Number 3, we have an electron current represented by this line here going towards the right. Well, everything I do here is vertical, right? For you guys, everything is going to be horizontal because it's on your page. You don't like horizontal? If it makes sense to you the way that I'm doing it vertically, then take your page and do this. Then all of a sudden, your page is vertical too. Okay, it doesn't matter what you do with your page. Okay, just don't do this. Just don't pick it up and do this when it's a test. Showing it to your neighbor. But you can orient your page any way you want, if it makes more sense that way, okay? Here we've got a wire that has an electron current going to the right. It's an electron current, so we're going to circle that electron and say it's going to be left hand, right? To remind us that, once we get into the heat of this, we don't want to forget and use our right hand for it. Left hand. Let's use this board marker right now as my current. Let's bring it out from the board just a little bit, okay? Because we have to get behind it, right? We have to get our fingers behind it. Well, it's difficult to get my fingers behind a piece of paper or behind the board here. So let's just bring the current out a little bit. Now let's say thumb in the direction of the current. Right now, where are my fingertips? Okay, you're always looking at your fingernails, okay? Where are they right now? Where are they? They're above the wire, right? If I do this, you can say, well, my fingers are above the wire, but not my fingertips. Okay, where are my fingertips right now? Sorry? Behind the wire. Yeah, that's not what I want right now. Okay, I want my fingertips, my fingernails. Paint them if you want. You guys should paint arrows on them. Paint arrows on your fingertips, okay? Do that. It's the cool thing to do. Everyone's doing it. Join the bandwagon. Maybe it started a trend here. Maybe everyone in the school will be like, hey, that looks kind of cool. Let's paint our fingertips with arrows on them. That's what we should do tomorrow, is have a little lab. A lab is paint everyone's fingernails, paint each other's fingernails. Thumb in the direction of the current. Fingers are right now above the wire. and they are into the page. So above the wire, we're going to say into the page. Right now, where are my fingertips? They're behind the wire. They're going to go down the page. Right now, this is where it starts getting tricky with your hand, especially if you have rotator cuff trouble like I do. You start doing this, start twisting it around. Where are they now? They're underneath the wire, and they're pointing out of the page. If this is the plane of my page, they're pointing out of the page. Right now, where are my fingertips? They're in front of it, and which way are they pointing? Up. Or let's say, be careful with this. Let's stop saying up and down. Let's say toward the top of the page. Why do I want to say that instead of up? Because if you turn your page, up is different, right? Does that make sense? Okay. This is up right now, but it's toward the top of my page. Okay. If my page is my frame of reference, then let's say toward the top of the page. Yep.
Will they always be like opposite each other?
Negatives and positives?
No, with the
Front and back?
as a paper, but yeah, like
Yes, yes. The question was, will say the front and back always be opposite to each other? Absolutely. Has to be. Right? If you think about how it works, right? My fingers go around. Well, if in the front they're pointing up, then they have to be pointing down on the back. Now, I would recommend doing the hand rule for each of them, even though you know it's going to be opposite, because there's a nice little check. Right? If it doesn't work out to be opposite, you know you've done something wrong in one of them or the other. Okay, worksheet number 10, question number 4. Says the diagram below shows the magnetic field, find the direction of the magnetic field surrounding this alpha particle. It's an alpha particle, so what do we circle? The word alpha, and then we write down RH, right-hand rule. Right-hand wire grasp rule. Let's use our right hand. Let's stick our thumb right now in the direction of the particle, which is up toward the top of the page. Where are my fingers right now? To the right side of it. Which way are they pointing? Into the page. Where are my fingers right now? They're behind it, and they're pointing which way? To the left. Right now, where are they? They're pointing towards they're to the left of the wire right now. And where are they pointing? Out of the page. And right now, they're in front of it, and they're pointing towards the right. Is it easier to do it vertically like that than it is horizontal on your desk? If it is, I think the only reason it is because that's the way you see me doing it, right? That's the way it's modeled to you. Okay. In the end, it doesn't matter. If we're using our page as a frame of reference, we're going to get the same answer whether we have our page like this, or whether we have our page like this, or whether we have our page like this. It doesn't matter. We're going to get the same answer. Okay? That's one little trick that you can use, too, as it starts becoming hard to contort your bodies to do certain things with the hand rules. One of the things that you can do is either change the position of the page or change the position of your body. And it ends up becoming a little bit easier sometimes. I shouldn't tell you that because, as I said before, it starts becoming entertaining for me to watch you trying to contort your bodies to make this work. But I shouldn't give you the out for it. All right, let's take a look at now question number 5. 5 goes back to the nice ones that are into or out of the page, so it becomes a little bit easier. This time we have an electron, so it's going to be left hand. And we have a magnetic field that points clockwise for an electron. And this time we're kind of going to go backwards, though. Instead of saying thumb, which way do my fingers point, this time we're saying fingers, which way does my thumb point? So left hand, fingers point clockwise, thumb must point out of the page. 6 is an alpha particle, so it's going to be right hand. Circle that. Once again, we have a magnetic field that's going this way. How do we make my right fingers go clockwise? Well, my thumb has to point into the page, so that would be an X, right? Is that good? You guys feel comfortable with that? It's what? Yeah, it's always cold in here, isn't it? Keeps you awake. All right. I think we've mastered that. At least I hope we've mastered that. We're going to do one more quick hand rule today, and then we're going to call it a day. There's not as much to this one, I promise you, but we're going to go through it, and then we're going to be ready to do our next hand rule, our third hand rule tomorrow. This one we're going to call the coil rule for solenoids. A solenoid, by the way, is just a coil of wire. It's a fancy name for a coil of wire. So if you've got a piece of steel or a piece of iron like this, and you've got wire wrapped around it, that's my coil, that's my solenoid. We've learned that that coil or that solenoid generates a magnetic field. The electric current generates a magnetic field. It'll magnetize the core inside it, the piece of steel inside it, and it becomes an electromagnet. But what's the polarity of this electromagnet become? Which end is north and which end is south? Here's my core that is ferromagnetic but not magnetized. Domains point in random directions, but it has the ability to become magnetized. Here's my wire that's wrapped around it. I'm trying to draw this in a good way so that you can understand what this looks like, but does that make sense to you? Okay, you get the wire looped around, and you can see the wire in the front of it, but then in behind the core, the wire disappears. Does that make sense? Okay, I'm not a very good artist, but I think that's okay. We're going to hook this up to a power supply down here. Battery. The short end of the battery is always the negative. The long end is always the positive. Don't forget that, okay? Usually, if you get that on a test, usually they label it, and they'll tell you which end is neg and which end is pos. You don't have to remember it, but just in case, let's remember the short end is neg, the long end is positive. Here's the way I remember it. There's two symbols. One's a negative, one's a positive. The positive is the one with the vertical line. The one with the vertical line has the longer vertical line. So the short end has got to be negative, the long end has got to be positive. That means the electric current leaves the negative end, goes around like this, up in the front, down in the back, up in the front, down in the back, and goes back around to the positive end like this. What's the polarity become? Here's what I would suggest you do for this. Take a piece of scrap paper or any piece of paper and make a solenoid out of it. Make a coil out of it. Just like this. Roll it up, just like this. And then do the coil rule, which is exactly the opposite of the wire grasp rule. In your textbook, by the way, they call them both the wire grasp rule. Yeah, I think that's silly because they work exactly the opposite of one another. I'm calling them something different. The wire grasp rule is the one we just did. The coil rule is the one we're about to do. If the wire grasp rule said, stick your thumb in the direction of the current, fingers in the direction of the field, this one's going to say, stick your fingers in the direction of the current and thumb in the direction of the field. So exactly the opposite. Thumb was current, fingers were field. Now it's fingers current, thumb field. Which way is the current pointing in front of this coil? Which way is it? Up. Yeah. So let's stick my fingers up. My left hand, because there's always going to be electrons in these problems. Left hand, fingers up toward the top of the page, right? See that? Which way is my thumb pointing? If the current is going up, the field, my thumb has to be pointing to the right. Now, remember that that's inside the coil. The magnetic field inside the coil will be the direction of my thumb, which is to the right. That means if I extended it, the magnetic field would go around like this. Tell me which end is north and which end is south. North is the right way, the right side, and south is the left side. The magnetic field inside goes from south to north, and outside goes from north to south. Make sense? Okay, once again, take your coil. If you know the current is supposed to be up in the front, then stick your left fingers up in the front. Okay? Thumb points to the right. Magnetic field inside has to go to the right. Done. Just label the polarity after that. We're going to do a couple more as examples, and then we're going to wrap it up for the day. Let me just summarize the rule there real quickly before we do another example. Okay? It was, for the last one, it was, let's summarize them both, actually. The wire grasp rule, it was thumb was the direction of the current, or the moving charge. Fingers, the direction of the magnetic field. For the coil rule, my fingers are the direction of the current, and my thumb is the direction of the magnetic field. The magnetic field inside the coil. Okay, let me draw another one here, just as an example here. Here's my core. Here's my wire again. Here's my battery. Which end of the battery is positive? Which end is negative? Left side is? Right side is? Good. The electric current goes this way. That means the current's going to go up in the back, down in the front. And then it's going to go back around to the battery like this. So far, so good? Okay, which way does the magnetic field point here? Let's make our coils. Okay, let's make our handy-dandy manipulatives here with our piece of paper. We're going to stick our fingers in front of the coil down. Okay, because I can see that the current in front of the coil is down. Now, if you want to do it behind the coil, because it's easier the way you're sitting there, it's fine. Just make sure that behind the coil, your fingers should point. If they're down in the front, they should be up in the back, right? It doesn't really matter. Okay, my fingers are down in the front. Which way does my thumb point? Towards the left. So that means the magnetic field is toward the left. The magnetic field inside the coil is toward the left. That means this would be what? This would be north, this would be south. Because inside, the magnetic field always goes from south to north. Outside, it's from north to south. Got it? We'll do one more example, and that's it. One more example here. This is the same one as last time, isn't it? Same as last time? Pretty much? Okay, don't draw this quite yet, okay? Which end is positive, which end is negative? Negative's on the right, positive's on the right, good. The electrons are going around like this. This should be the same answer as last time, right? Let's make my coil here, okay, with my piece of paper. This time my fingers should go in the front. They should go up in the front. Which way is my thumb pointing? Towards the right. How's that possible? This is going to be north, this is going to be south. The last time we said the right end was south. This time we're saying the right end is north. We have our batteries set up the same way. How do we get the exact opposite magnetic field? How do we get the polarity reversed? The wires are coiled differently, yes. The wire in this one you can see is coiled, kind of goes up in the front, right? In this one it's the exact opposite. So of course, although the direction of the current is going to be the same, you're going to find the polarity of the electromagnet is exactly the opposite. Was that perfect timing or what? Okay, have a good night, everyone. Make sure you have this copied if you don't have it copied now. We'll see you tomorrow.